transient formation. Of an enzyme substrate covalent complex. Okay, so your enzyme and your substrate, they form a covalent bond between each other. Typically what happens here is that your enzyme is going to nucleophilically attack your substrate. And because of that, this is also called nucleophilic catalysis. So nucleophiles, what do I need to be a nucleophile?
Lone
Lone pair of
pairs.
electrons. If you're negatively charged, that helps. Makes you a stronger nucleophile. But I gotta have a lone pair. And so when looking at your enzymes and what sorts of things can act as nucleophiles, great, I have an OH. It could be a nucleophile. If it gets deprotonated in the process, then it's even better nucleophile. But what sorts of enzymes have hydroxyl groups on? Serine, threonine, and tyrosine. Phiols, cysteine, primary amines, sorry, lysine, and then if I have an imidazole, there's only one thing that can be histidine. Okay. And so these are typically the amino acids that you see acting as nucleophiles in covalent catalysis. We're going to do the example specifically for a lysine. As lysines can form shift bases. So if I have an enzyme, and I suppose this could also be an N-terminus here, but we'll say it's a lysine side chain that has that primary amine. And then if my substrate has got some sort of carbonyl group on it, then I have the opportunity to make a shift base. How many remember talking about shift bases in organic? So we are going to do some really bad organic mechanism drawing here. We're going to do the biochemistry version, which is take all those individual steps and cram it into one picture.
Yes.
And I just want you to know that is bad habit. That if an organic chemist went and looked at this, they yell at you for doing it this way. But when you look in biochemistry textbooks, biochemists, I guess, we're lazy and we don't like drawing all those extra steps. So we're actually going to take 3 steps and we're going to cram it off into one. Okay. In order for this to nucleophilically attack the carbonyl, if I want to make the carbonyl a better electrophile, what do I do to it? That's the hint.
Add a hydrogen to the
Okay,
oxygen.
we're going to carbonate it. So we're going to carbonate it
Yeah.
to make it a better electrophile. My nucleophile then can attack there, which would pop this open. And to make the nucleophile a better nucleophile, I would
Deprotonate.
deprotonate it. Okay, so this is crazy because there's not an organic chemist alive who would ever draw it like this. Okay, we would first draw the protonation step, and then we would draw the nucleophilic attack, and then we would probably deprotonate the nucleophile after it had already attacked. So, yeah, I'm going to let you be sloppy. Okay, so then I end up with my enzyme that is covalently bound to my substrate. So the next thing that happens is actually the formation of the shift base here. That we're also going to draw in multiple steps so that we never happen this way. Okay. So I end up forming the imine, and my water is basically leaving, but to do that, it has to get protonated via water. So again, we're just cramming lots of steps together. And now I have this. Okay, this is a shift base. This is a common type of enzyme substrate covalent complex. Not the only kind, but it's a common one. And we will see examples of other types as we go. This is completely reversible. Basically, you just hydrolyze it with water. So all those steps we just drew can go backwards. Okay, and so water nucleophile carbon pops those electrons back on the nitrogen. And what's great about these things is that they provide an electron sink. Promote bond cleavage. So this little positive charge on the nitrogen, it likes to pull electrons towards it. And so if you form a shift base during your reaction, it's a great way to promote carbon-carbon bond cleavages. And that will make more sense when we do the first example. For example, a decarboxylation. So first we're going to do an uncatalyzed reaction. Take acetoacetate, and there's an enolate intermediate before you get to the acetone product. Okay, so this is my acetoacetate. And in a decarboxylation, I am removing a carboxyl group, and I usually do that by eliminating carbon dioxide. And so in this first step, we lose CO2, but there's some shuffling of electrons that has to happen here to make that happen. So we end up moving electrons from oxygen to form the double bond there. Can't make 5 bonds to carbon, so that actually caused breaking of this one. And we're going to do another bad organic habit. So, don't let Dr. Bruno and Dr. Russell catch you doing this. We're skipping steps here. So we have to break that bond. And then that will be up on the oxygen, and so then we end up with the enolate.
Is that part of the oxygen?
Yeah. Sorry, my arrow's going the wrong way. Okay, so that is my enolate, which is a high energy intermediate. And then in that last step, we're going to bring in a proton. And we're basically going to let that collapse and then move that back onto here, but then it gets protonated to make the ketone. And between the enol and the keto form, which is the more stable form, the keto form, right?
So why is it being called a sink?
We haven't gotten there yet. So this is the uncatalyzed reaction. This is what would have to happen if you had no enzyme around. Okay, so now we're going to do the catalyzed version where you do have the enzyme around. So catalyzed reaction. So this is going to happen in 3 steps. So we're going to get nucleophilic attack by enzyme, form your covalent intermediate, and then you get withdrawal of the electrons from the reaction center, and that's done by the electron sink. These are shift base. To promote the decarboxylation, or in our case, loss of CO2 in this step. And I'll say reaction, because that's generic, and then for our specific example, it would be loss of carbon dioxide. And then the last thing is going to be elimination of the enzyme from the complex, so this is going to reverse step 1. Okay, so start with the same substrate. Start with acetoacetate. And in the first step, the enzyme comes in, which I'm just going to use an E now. And it has that amino group on it. And that's going to come in, and you're going to see this a lot in arrows. Something coming into the arrow, and then sometimes something leaving. And in this case, our something leaving is going to be OH minus or water. And that is what we just drew before on the previous page there, is that formation of the shift base. Okay, so instead of the carbonyl, or inside of the carbonyl, we're going to put in our imine, and it's going to be that carbonyl that is attacked. So then I get my shift base. The electron sink. Okay. So the electron sink is just that positive charge on the nitrogen. And in the very first step of our decarboxylation, so I'm going to go back up here to where we saw the decarboxylation. We had to move these electrons towards that carbonyl. We put those electrons up on that oxygen. And yes, oxygen is electronegative, so it is going to pull electrons towards it. But between pulling electrons towards an oxygen and creating a new formal charge, or pulling electrons towards a positively charged nitrogen to eliminate a formal charge, which one is going to be a more positive type of reaction?
The second one.
This one, the second one, yeah. So we're creating something more stable and more likely to promote that bond cleavage. So now, again, we're going to get this, and we're going to get that, and we're going to get that. So decarboxylation occurs more readily because electrons are pulled towards the positive charge. Okay, so then if we go down this direction, CO2 leaves. And I'm left with my intermediate again. And I skip a step. No, we're skipping steps. So again, this is my intermediate. So it's a more stable intermediate than what I had before. And then, again, I do have to have a proton come in here, and I'm going to reform the shift base. And the last step is water comes back in. And this is, again, my reverse reaction to reform carbonyl. So again, we're skipping a lot of steps here. Just draw mechanisms all day otherwise. And you get your acetone. And what comes out is my enzyme. So again, if you're looking for evidence that covalent catalysis is taking place, you're looking for some sort of intermediate where your enzyme is covalently bonded to your substrate. Okay, and this is just one example, and we're going to see more as we go. Yep.
So is the shift base like the ending with the enzyme, or is it just like the, like what's the actual shift base itself?
The actual shift base is this imine structure here, and I know it's actually the conjugate acid of the base, but that's just what people call it, is when you have that imine with the positive charge on it, that is a shift base.
Okay.
Yep.
Because water comes in.
Oh, please don't make me balance.
Oh, sorry.
That's okay. I mean, it's a so your enzyme comes in, and so if you want to make everything balanced, then it's probably water that has to leave at that point, and then because water comes back in at the end. But there's a bunch of protonation, deprotonation steps, and I wasn't bothering to keep track of any of those. So it's fine. Water's around, you can deprotonate or protonate to your heart's content. Metal ion catalysis. the method for the catalysis or the mechanism can differ. So it's usually easy to spot that, yes, there's an essential metal needed for catalysis, but there's lots of different things that metal could be doing. So there are kind of different types or different subcategories underneath metal ion catalysis. So you could have metal ion catalysis where you're binding the substrate. To orient it properly. And in this case, we're talking about coordinate covalent bonds, which we are distinguishing from regular covalent bonds. So if it's a coordinate covalent bond, it goes under metal ion catalysis, not covalent catalysis. So it's coordinate covalent bonds. Okay, so that might be what it's doing. It might mediate redox reactions by accepting or donating electrons. Okay, so iron is a great example of that because you can have a +3 or a +2 oxidation state, and so it can help out in redox reactions by donating electrons or taking them on. It could stabilize intermediates. By shielding or stabilizing negative charges. So it could just be a case that you've got a bunch of highly unstable formal charges and you need some sort of positive charge to offset that. So if you have a positive charge on the metal, that can stabilize negative formal charges on the substrate. So it might be stabilizing, or your positive charge on the metal may shield negative charges from incoming nucleophiles. So if your reaction involves a nucleophilic attack of some sort, but your substrate has a lot of negative charges on it, that nucleophile is going to get repelled because you got electrons coming into electrons. So one way to allow that nucleophile to come in more easily is to put positive charges near those negative charges to shield them. And we'll see examples of that too as we go, especially second semester. Okay, and then the last thing it could do is it could make waters more acidic. So basically it's going to make water a better nucleophile. And that's something that you see, that when water is coordinated, or if the metal is coordinated by water, the pKa on the water actually drops. And so waters that are coordinating metals are more acidic than waters that are not. Okay. So we'll do an example of that last one. Carbon dioxide plus water. This is a reaction you've done. Make some bicarbonate and some protons, and there is an enzyme in your blood that you need to make that happen. Carbonic anhydrase. Ca is coordinated by 3 histidines in the enzyme and by water. The 4th histidine extracts the proton from water and this is easier to do because it's more acidic. More acidic than normal. And then your hydroxide that is formed can nucleophilically attack the carbon dioxide. So you have a zinc, 2+ charge there, and this is being coordinated by those histidines. The histidine has a nitrogen on its side chain that can donate a pair of electrons to coordinate it. And then we also have water here. But because this is now more acidic, another histidine out here can grab that proton and then, again, we're combining steps. We're always combining steps. If I have some carbon dioxide here, then these electrons can attack there. And now I have zinc. Oh, sorry. I started writing myself. And bicarbonate.
Dr. O,
Yeah.
is that one on top of this thing?
Yeah, sorry, I started writing imidazole. So histidine, histidine, histidine. Yep. But you need to remember here, active sites must be regenerated, otherwise it's not a catalyst. Okay, so to regenerate that active site, what am I going to have to do? I've got to bring in a new water molecule. Yep, and what did I change over here?
Deprotonate the
Yeah, I got to
histidine.
deprotonate that histidine. So once this has happened, that's great, but there has to be a system in place to regenerate your active site so it looks like it just did at the beginning. So another water molecule coming in, no problem. Deprotonation of the histidine is probably also through water, very likely. Because remember, histidine has got that pKa pretty close to physiological pH, and so it's very easy for water to come in and deprotonate. I think I have a picture of this one. That shows all the coordinating groups. So there's my middle zinc, and here's my 3 histidines that are coordinating the zinc, and then I have my water. And then there's another histidine that's going to pull off a proton. I don't think it's that one. I think it's another one they're not showing in the picture. But that water will be more acidic, and so it's much easier to pull out that proton, and then hydroxides will be well. Okay, so those 3, acid-base catalysis, covalent catalysis, and metal ion catalysis, are probably what we're going to mostly focus on, but there were 2 more. So proximity and orientation. Catalysis. Again, not to be confused with the metal ion, because metal ions can have proximity and orientation effects, but when it's a metal ion, we call it metal ion catalysis. But sometimes there are enzymes out there whose job it is just to bring substrates together. So enzyme brings the substrate, and then in parentheses there, substrates, into contact with your kind of catalytic groups or reacting groups. In some cases, the enzyme doesn't perform any type of kind of chemical catalysis. All it is bringing the substrates close together, so the functional groups are close. And then once the functional groups are close, they can react like they would in an uncatalyzed reaction. You are basically restricting translational and rotational motion. And so this is basically improving your odds of collision. And these kinds of effects can raise reaction rates by in the order of magnitude of 10 to the 7, just by restricting that motion. Okay, so here's the thing. Almost all enzymes, the reaction rate is going to be affected by its proximity and orientation effects. That's going to be true for any enzyme. However, there are some enzymes that function only by proximity and orientation. And so, you know, if you say proximity and orientation is the type of catalysis happening for this particular enzyme, you're not wrong, but it might not be the most significant thing. Okay, so we're going to have lots of examples where you're shown a mechanism and then you're going to be asked to describe what types of catalysis are taking place. So if you say this one, you'll be wrong, but it might not be the best answer. And then the last one is the hardest one to know. So preferential transition state binding. And in this case, the enzyme binds more tightly to the transition state than to the substrate or the product. So binding to substrate promotes the conformational change you need to go to the transition state. So when the enzyme binds to the substrate, that affinity might be weak, but since the enzyme will bind tightly to the transition state, it will actually force the substrate to adopt the new structure, something that resembles the transition state. And that helps to push that reaction forward. This is hard to identify unless you already know something about the mechanism. So if you're trying to figure out a mechanism from scratch, you aren't going to immediately know, oh, this is catalysis by transition state binding. No, there's a lot of work that has to go into figuring out whether the transition state is involved in promoting catalysis. However, these are the most vulnerable to inhibitors that mimic a transition state. So and again, we'll see some examples of these as we go along, where you have some sort of transition state analog that ends up being a very good inhibitor. And when we look at lysozyme, we'll see one of those. So again, this is something that isn't so easy for you to know, looking at a mechanism from scratch, whether that kind of catalysis is going on or not. But we will look at our case studies, and I'll point out when that type of catalysis has occurred. Okay, how are we doing? 5 types of catalysis. One enzyme mechanism. So group activity, there's an enzyme mechanism on the back. There we go, on the back. And then there are a bunch of questions that you need to answer about it, and it is going to ask you to identify the types of catalysis taking place and the residues involved in the enzyme for the type of catalysis. I love these questions. There will be a question like this on the exam, guaranteed.